Hello and welcome back to Math Class in Session. Continuing with quadratics, solving linear quadratic systems. A linear quadratic system is a system of two equations that are both true at the same time. That's what a system of equations is. Two or more equations. One of these equations is linear and the other one is quadratic. And in grade 10 they were both linear. Remember lining them up for elimination or doing substitution with the two linear equations? Now, one of them is quadratic. That's the only difference. A linear quadratic system can have two solutions, one solution, or no solutions. As in, here's one with two solutions. We have a line and a quadratic, two solutions, meeting in two places. Where they meet are the solutions. We can have one solution, so they can meet just once, or we can have no solutions. Now, what I'm going to show you is a second-degree relation which behaves very much like a quadratic. This is a second-degree relation. It's a circle, and this is a line that completely misses the circle, and so there's no solutions here. Example. Let's solve a system of equations by graphing. Okay, here's our quadratic and a line, two equations that are true at the same time. Let's find out if and where they meet. Solution: prepare the equations for graphing. Let's start with the parabola. I copied it, and now we have to complete the square to find the vertex. So that means factor out the -2 out of the first two terms. And let's check our work. -2x squared looks good. -4x looks good. And take the coefficient on x, cut it in half to 1, square it to 1, add it, and subtract it. Close the brackets, and this +1 remains outside. Removing the fourth term and distributing the -2 into the bracket to remove this fourth term. And repackaging the square. This is a perfect square, so we can express it as a square of a binomial, and combining these to 3. We have our vertex at -1, 3. Taking the line, preparing it for graphing, let's isolate y. Y equals -2x minus 3, kind of looks like mx plus b, and we're ready to do the graphing. Bringing it all forward to a grid. Here's the result of our work, and we'll graph these two functions. We'll start with the parabola, go to the vertex at -1, 3, and put a point there at -1, 3, which is right there. And displacing over 1, and go down because it says minus here, so go down. If I go over 1, I would expect to go down 1 squared. 1 squared is 1, but wait, times 2, because we're going to multiply by 2. So over 1 down 1 squared times 2 takes me to there. Now, I notice we have the y-intercept here at 1. If I were to bring forward the original parabola before we completed the square, it looked like this. And we can see that this number on the end was +1. So that's consistent with that being a y-intercept of 1. Because of the axis of symmetry, which is a vertical line through the vertex, a point must appear over here as well. Back to the vertex, over 2, displace down 2 squared, because if I displace 2 over, I have to go down 2 squared times 2. 2 squared is 4, 4 times 2 is 8, so from this point, count down 8. Well, 3 takes me to the axis, and 5 more takes me right here. Put a point there. And because of symmetry, a point must also appear here. Draw a line through them, and that's the parabola. Next, let's graph the line with a y-intercept of -3. This is mx plus b, so y-intercept of -3 right there. And the slope mx, the coefficient on x, is -2. So that means drop 2, run 1. So drop 2, run 1 puts a point there. And we could back this pattern up. Go to the left and then up 2, go to the left and up 2. So we could back the pattern up a bit, just in case we need to take a ruler and carefully graph a line through those points. There it is. And now the solution is where the blue line and the red line meet. And they meet at -2, 1, and they meet at 1, -5. We can see them here. Let's do it again. Solve a system of equations by graphing. Solution, prepare the equations for graphing. If I see x squared over 2, then I see 1/2 x squared. Perhaps this is easier to think about. Now, common factor out 1/2. Whatever's on the x squared gets common factored out. So I have to divide out 1/2 out of 3, which makes it into a 6. And take the 6, cut it in half. That's 3, square it. That's 9. Add it and subtract it, leaving the -1/2 out. And removing the fourth term, 1/2 times -9 will be -9/2. So I've removed the fourth term. Repackage the square. Well, I claim it's this. Let's check. Square the first term. Double the product. -6x. Square the last term. -3 squared is +9. And -9 minus another 1 makes -10 over 2, and that's -5. Take the linear equation, prepare it for graphing. Here's the linear equation. Isolate y, and we have y equals -x plus 2. Looks like mx plus b. Carrying them forward to a grid. Here's our work. Let's start with the parabola again. Go to the point 3 minus 5. Let's carefully go to 3 minus 5 and put a point there. Now, graphing a parabola from this point. Displace 1 over, go up 1 squared. 1 squared times 1/2, that is. And 1 squared is 1 times 1/2 is just 1/2. And because of symmetry, a point appears over there. Back to the vertex over 2. Up 2 squared times 1/2. 2 squared is 4. 4 times 1/2 is 2. So right there, a point appears, and because of symmetry, a point appears here. Back to the vertex over 3. Up 3 squared is 9. 9/2. That's 4.5. 1, 2, 3, 4.5. A point appears there. And because of symmetry, a point appears there. And here's our y-intercept again. Y-intercept. Before we completed the square, this parabola looked like this. And we can see that the y-intercept is this number on the end. Yes, indeed, it's -1/2. So everything is consistent then. Back to the vertex over 4. 1, 2, 3, 4. Up 4 squared times 1/2. 4 squared is 16. 16 halves is 8. So count up 8. Well, 5 takes us to the axis, and then 3 more. Puts a point right there. And because of symmetry, a point appears right here. Draw a line through all these points, and we have a nice parabola. Graphing the line, starting at the y-intercept of 2, so a point appears here. And then I notice that the slope is -1, the coefficient on x. So we'll drop 1, run 1. Drop 1, run 1. It's easy, so why not do it a couple of times? Take out a ruler and draw a line through those points carefully. And we get that line. And where the blue line and the red line meet, we have our solutions. -1, 3, and 5, -3. And we can read them right off the graph. Let's do one by algebra. Now, I've presented here a second-degree relation. It's a circle centered at the origin with radius √10, which is just a little more than 3. This is a second-degree relation. It's not a quadratic, but it behaves in the same way as a quadratic when it's part of a system of equations with a linear equation like this one. So we'll treat it just like we would treat a quadratic, even though it's a second-degree relation, which is a circle in this case. Solution, Our solution method is to substitute the linear equation into the quadratic, or in this case, the second degree relation. So to do that, we have to prepare the linear equation. There's the linear equation. Isolate one of the variables. I could have isolated x, but that would have involved fractions. I've got a singleton y to work with here, so why not isolate y? Y equals minus 3x plus 6, and that has to be plugged in to the second degree relation. So see this y? It's going to become this. We use brackets for that. And now we're squaring a binomial, which means the first term squared and double the product and so on. Here it is. The first term squared is 9x squared. Double the product here. We get negative 18 doubled is minus 36x, and then plus 36. Collecting up like terms and equaling it to 0, because it is a quadratic equation. So we like them equal to 0. We can divide through by 2, just to make the numbers a little smaller, and then we can solve by factoring. You need to be able to factor that quadratic, and it becomes that. And then setting these individually equal to 0, we have x equals positive 13 over 5, or x equals positive 1, when we set the factors individually equal to 0. And now, taking the x-coordinates of our solution and plugging them into one of these. How about this one? Looks inviting. Minus 3x plus 6, plugging those two in, we get these points. When you plug the 1 in, you got minus 3 times 1 plus 6, which is this 3 here. And when you plug in 13 fifths and do the math, you get negative 9 fifths. Those are our solutions. Let's take a look at this on the graph. I graphed the circle, x squared plus y squared equals 10, a circle of radius root 10, which is a little more than 3. This is the line, the red line is the line, and there's our solutions. 1, 3, 1, 3. This is the origin. And 13 fifths, negative 9 fifths. 13 fifths is 2 and a bit, 2 and 3 fifths, in fact. And negative 9 fifths is negative 1 and 4 fifths, so it's down here. So we can see the solutions, we can see the graph, and this is what we've done with the mathematics.